When we did our analytic analysis of the constraint conditions between the accelerations of objects 1 and 2, we came up with a condition that a1 was equal to minus 2a2. Now let's do something which we call a virtual displacement argument. Suppose that b and 2 move down a certain amount. Let's imagine, and I'm going to draw it in a different color 2. So we have object 2, and pulley 2 has moved down. Now, this object has displaced by a distance delta y2, which is also equal to delta yb because they're connected. Now, what happens when the system does that is our rope has to extend downwards around this pulley and come back up. And that means that the rope, that object 1 has been foreshortened by not just delta y2, but on both sides, delta y2 and delta y2, object 1 has displaced up by that amount. So we'll just make this so we can draw it in a reasonable way. So what we see here is that delta y1 is equal to, now notice if 2 goes down, y by delta y2, then delta y1, which is this whole distance, is a negative quantity, and it's going upwards, and so we see that that's minus 2 delta y2. And if we took two derivatives, or displacement, and then look at the change in displacement, we would see that this implies that the acceleration of 1 is minus 2a2. But let's come back to our two conditions for length and see the same thing here. Because delta L2 is 0, this tells us that delta y2 is equal to delta yb, so we'll write minus equals 0. And that was our condition, that the block and 2 are moving together. And up here, we see that because delta L1 is also 0, this implies, and now I'll make that substitution, that delta yb is equal to delta y2, that 2 delta y2 here and here plus delta y1 has to be 0 coming from that piece. And so we see that delta y1 is minus 2 delta y2, which is what our virtual displacement argument showed us. And again, if you take two derivatives, here we have that, recall that in the simplest way, that the velocity is dy1 dt, and the acceleration, a1, is d squared y1 dt squared, then the same proportionality is maintained under the two derivatives. And that's another way of thinking about how to get the relationship between the accelerations, but you have to be extremely careful about that sign, because as 2 goes in the positive direction, 1 will go in the negative direction. We are now in position to find the accelerations a1, a2, and the tension, because we have Newton's second law and our constraint condition for the acceleration. Let's recall the equations that we found. We had m1g minus t was m1a1, and we had m2g minus 2t was equal to m2a2. And we also had the constraint condition between the accelerations that a1 was minus 2a2. So now we have a system of 3 equations, and we can solve for any of these quantities that we want. So one way to do it is to identify an equation and to identify a quantity that we would like to solve for. So for instance, let's identify that we want to solve for a1 first. So how are we going to develop a strategy for that? Well, I'll choose equation 1 as my backbone equation, and I have an unknown t, but in equation 2, that unknown t is appearing there, but it's expressed in terms of a2, and a2, though, from equation 3, is expressed in terms of a1. So my first step is to rewrite equation 2 as m2g minus 2t equals m2. Now here's I'm going to make the substitution, which is minus a1 over 2. So we'll call that 2a. And now I have equation 1 and equation 2a, two unknowns t and a1. And what I can do is I can solve for either equation, and I can make a choice what's easiest. When I look at these equations, it's easiest for me to identify what t is in terms of a1. So I'll write m1g minus m1a1 is equal to t. I'll call that equation 1a. And now I can substitute that value of t into equation 2a, and I get m2g minus 2 times m1g minus m1a1, and that's equal to minus m2 over 2 times a1. And now I'd like to collect my a1 terms. And what I have over here, let's bring all the a1 terms to this side, and I get m2g minus 2 m1g. I have a plus, so I'm going to bring that over to this side, and I get equal to, that's plus plus, so I'll have two minus signs, and I'll have 2 m1 plus m2 over 2 a1. And now I can solve for a1, and what I get is I get 2 m1g minus m2g, and I want to divide through by this denominator. And what I have downstairs is 2 m1 plus m2 divided by 2. And that's my expression for a1. Once I have that expression for a1, I can easily come back and find out what a2 is, or I can substitute into the equation here for a1 and find out what the tension is. And so I can now easily find my expressions for a2 and t, but I'll leave that as an exercise.
We want to look at this pulley system. We want to find out what this force here is, for example, with which this block is being pulled. Now we have two massless pulleys here and two moving parts. And one key component of this problem is to derive the acceleration constraint. How we're going to do that? Well, we have to look at this string here. First of all, it's a fixed string length, and that will help us. Ultimately, this is just a distance that connects all of these objects. And if we eventually differentiate that twice, we get to an acceleration. So the first thing we're going to do is to derive figure out what the string length is, to then derive the acceleration condition. Let's begin by first identifying the fixed length in this problem. So we have a little distance here. We call it SB. And we have a distance here that's fixed SA. And we furthermore know that this block here is fixed to the ground, and we can choose a coordinate system origin. Let's say we do that here. We know that we have the distance d here to this little block. The moving parts are block 1 and block 2, so we have to assign position functions. And actually, this one here is x1. It goes up to here because we want to measure the string length ultimately, and we know this portion here, so we can subtract it. And then, of course, we need also x1 that goes here, x2. So now we can tally up the length. Let's start with this portion here. That is d minus SA minus x2, e minus SA minus x2. And then we have a half circle here, pi r, and we know actually that there's another half circle going to come there, so we can just write 2 pi r immediately. And then we have this part here. That one is x1 minus sb, and then minus sa minus x2. And then finally we have this portion, and that is x1 minus sb minus x2. Okay, so the next step is that we need to simplify this a little bit. So we have one x1 and another one here. 2x1 plus x2, 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 actually 3, minus 3x2. And then we have all sorts of constants. We have d, we have sa, sb, the 2 pi r. But as you will see, if we differentiate this L here, that will actually all fall away. So we're going to make our life easy and just add a constant here. And so we want to now do the second derivative here of our string length with respect to time, because these are all position functions, so we can differentiate those. What's important, of course, here is the string length is not changing with time. So actually we know that that derivative will be 0. And we can just write this up here because x differentiated twice is a. So 2a1 minus 3a2. And we immediately see from that that a1 equals 3/2 a2. So this is our constraint condition that we will need later. For now, we need to continue with setting up free body diagrams of all 4 objects. Let's start that with object 1. What's acting on object 1? Well, we have F here. We're just going to write it as magnitude. We have F, and then we have here a tension that goes to the pulley B. That one is different from the tension in the string, so we're going to call this TB. Then we have object 2. And of course our I hat goes in this direction because it follows the motion of the objects. We have here kind of the reverse. Now we have a tension of this string here that's attached to pulley A, but it's different from the string tension. That's a specific one, TA. And we also have a T from the string here, so we'll add a T. And then if we look at pulley A, we have 2 string tensions, T and T, and here we again have a TA, and pulley B, TB, and 2T over here. So that means we can write down our equations of motions using Newton's second law. F equals ma. And since this is just going in the I hat direction, we can just write down the 4 equations following the 4 free body diagrams here. So we have F minus TB equals M1 A1. We have T plus TA equals M2 A2. Then we have 2T minus TA equals 0. That is 0 because we are dealing with 2 massless pulleys there. That means M is 0, and so our acceleration term is 0, so the m is 0 here. And finally we have tb minus 2t, oh, not 2 pi, 2t. And that one is also 0 because it is a massless pulley. So here we have our 4 equations of motion that fully govern this pulley system. And we can use it then, for example, to find this pulling force here. We know what TB is from the equation down here, so 2T. We know what TA is, it's also 2T. And we can then solve this for F. The only sticky part is that we have this A1 and the A2 in here, but for that, we derive this constraint condition here. So with that one, we can fully solve this. Otherwise, we would have one too many unknowns. Alternatively, if one were to be interested in one of these accelerations, then this equation system can also be solved for A1 or A2.